Systems fail. That is a fact. The real question is not if a failure occurs, but how the system reacts when it does. How can a system detect a fault early enough, and how can it respond in a way that keeps the system safe? This is exactly the role of safety mechanisms. In this video, we explain how safety mechanisms work in ISO 26262 and how they are used to detect and handle faults in real systems. Why are safety mechanisms so important? In complex systems, faults cannot be completely avoided. They will occur. The critical question is whether these faults are detected and handled correctly. If a fault remains undetected, it can lead directly to a hazardous event, and this is exactly what must be prevented. Safety mechanisms reduce this risk significantly. They ensure that faults are detected early, and that the system can respond in a controlled and safe way. And as ASIL levels increase, the importance of safety mechanisms becomes even higher. So what are safety mechanisms? Safety mechanisms are functions within a system that detect and handle faults. They are implemented in both hardware and software. Their purpose is to continuously monitor system behavior. If a fault is detected, they trigger a defined response to maintain safety. In simple terms, safety mechanisms ensure that faults do not lead to hazardous situations. They are a fundamental part of functional safety in ISO 26262. Safety mechanisms can be divided into two main types: fault detection and fault handling. Fault detection identifies abnormal system behavior. It answers the question, is something wrong? Fault handling defines how the system reacts. It answers a different question. What should the system do when something goes wrong? And this distinction is important. Detection alone is not enough. A system must also react in a safe and controlled way. Let's take a closer look at fault detection mechanisms. The goal of fault detection is to identify abnormal behavior in the system. This is usually done by monitoring signals and comparing them to expected values. For example, a system may compare a measured signal with a calculated or redundant signal. If the values deviate beyond a defined threshold, a fault is detected. This is often referred to as a plausibility check. So here's a simple question. How does the system know that something is wrong? By continuously checking whether the behavior matches expectations. Once a fault has been detected, the system must respond. This is the role of fault handling mechanisms. They define what the system does after a fault is identified. In many cases, the system transitions into a safe state. This could mean limiting functionality, switching to a fallback strategy, or shutting down certain components. The goal is always the same: to prevent hazardous behavior and maintain safety. Let's look at a simple example. Consider a system that uses two sensors to measure the same parameter. Both signals are continuously compared. If the values match, the system continues normal operation. But if there is a deviation beyond a defined threshold, a fault is detected. Now the system must react. For example, it may switch to a fallback strategy or transition into a safe state, so detection and handling work together to maintain safety. Safety mechanisms are closely linked to ASIL levels. As the required ASIL increases, the need for robust safety mechanisms also increases. For lower ASIL levels, basic monitoring may be sufficient. But for higher levels, especially ASIL-D, multiple layers of safety mechanisms are required. This includes redundancy, advanced monitoring, and fault handling strategies. So, higher risk leads to more complex and more robust safety mechanisms. There are several common mistakes when applying safety mechanisms. One of the most common is relying on detection alone. Detecting a fault is not enough. The system must also react correctly. Another mistake is assuming that monitoring is always sufficient. Monitoring can fail as well. So safety mechanisms must also be designed to handle their own potential failures. Some systems also lack independence between mechanisms. And finally, implementing mechanisms without proper validation. A safety mechanism is only effective if it is verified and tested. Let's summarize the key points. Safety mechanisms are used to detect and handle faults in a system. Both detection and handling are required to ensure safety. These mechanisms are implemented in both hardware and software. As ASIL levels increase, the need for robust safety mechanisms also increases, and they are essential to maintain safe system behavior under all conditions. If you want to go beyond this introduction to safety mechanisms, we offer comprehensive online training programs on ISO 26262 on our website. These self-paced courses cover safety mechanisms, ASIL, HARA, and system design in a structured and practical way. The focus is not only on understanding the concepts, but on applying them in real engineering projects. You can find the link in the video description and also in the pinned comment below. If you found this video helpful, feel free to give it a like and subscribe to the channel. We regularly publish content on functional safety, ISO 26262, ASIL, ASPICE, and other engineering standards. Thank you for watching, and we look forward to seeing you in the next video.